What is going on, everybody? Welcome back to another podcast episode. Thanks for joining us on the Civil Engineering Academy podcast. Appreciate you being here and listening. Definitely check out our website if you haven't done that already, if you need help on your journey to pass your FD or PE exam, but also give us a like and a share. Appreciate you sharing this stuff with friends or neighbors or anyone else in the space of civil engineering. We love sharing this stuff with you. So I'm excited today. We got a good episode. Seismic stuff, it seems to be on the forefront of engineers' minds as we hear more about seismic events in the world. And recently there was a test. They've been doing testing called the Tallwood Shake Test that happened in San Diego. And I wanted to bring my brother Mark on to talk about this test and really hear about the direction of where we are going as an industry in using wood in our building material and use for structures and how high we can go. So without further ado, let me bring Mark on. Hey, I wanted to jump on real quick and let you know about a free resource we developed for you. You can find it at civilengineeringacademy.com/PE guide, and this will help you to jumpstart your studies for your PE exam. So if you're in the hunt and you're just thinking about the PE exam, this guide will help you get through the process of figuring out everything you need to do, from the PE exam's prerequisites that you got to figure out, the must-have materials that you're going to need for the exam, any approved calculators, what groups you should join, exam secrets, and much more. It's all in this guide that we've got developed for you. It's completely free. You can go check it out at civilengineeringacademy.com/PE guide. Just put in your email. We'll get you that information as soon as the email comes to your inbox. So go check it out, civilengineeringacademy.com/PE guide.
Hey, Isaac.
Mark, what is up?
Hey, I'm back. You're always bringing me on. It's always a good time, Isaac.
Yeah, man, you're a regular. So this is good.
I love it.
Well, this is awesome. We kind of connected over another article that we were reading about some seismic testing that was done called the Tallwood Shake Table Test that was performed in San Diego. UC San Diego was running that event, and they were able to, I think, build up to a 10-story building. So I don't know, Mark, do you want to give us a little bit more background as to the significance of this thing?
Yeah, so UC San Diego's always had this big shake table, right? And so their idea is to build a full-size mock-up of a building, and then start shaking it, right? Simulating actual seismic events, actual frequencies of seismic events, and then get a real live full-scale test result on how the structure performs. And so what they've typically done with this shake table is look at buildings that are framed with wood, right? So you might think of a typical single family home, right, as kind of the typical structure that's framed with wood, and we typically use dimensional lumber for that. Sometimes we use engineered products, right, like laminated timbers, and those perform very well, but they're always kind of smaller scale things. So they're testing capacity of wood shear walls, right, which are basically just segments of the wood framing on a wood structure that have a type of sheathing, maybe an OSB that's got certain nailing requirements, right? It's got hold downs on the corners that have to perform at a different level. Sometimes those hold downs, we call them in shear wall applications or vernacular, we call them boundary elements, right? Those shear walls have to be tied down. And so they've modeled these smaller scale items that are mostly geared towards single family homes, right? And the design of those things. Well, now, with cross-laminated timbers, or CLTs, which is another engineered product where they take dimensional lumber and they machine it, right? They join it and glue it all together into different size panels that they can create floor structures, and then they glue it together into big columns where they can create vertical elements, and they can build pretty high structures with this with the CLT systems. And so Traditionally, wood structures by the code have been limited to a certain height by the code, just because they can't get too high, because of the code restricts. It's a combustible material, right? Wood is a combustible material, and so they restrict the height of buildings that are built of combustible material, because they want people to be able to get out of the building in time before the thing collapsed because of a fire, right? And so when you start building structures out of wood that are taller than 5, 6, 7, 8 stories, the fire ratings and the burn rates on your structure start becoming an issue. And so, but now with the CLT technology, they're starting to get past the fire problems. And so now they're looking at things structurally and saying, okay, if we do go higher, and we build things with CLT, how's it going to perform? And so that's kind of the impetus behind this Tallwood Shake Table Test.
Could you touch on the resurgence of tall wooden buildings in modern construction? Like, what is the drive here to test stuff and build stuff out of wood?
Yeah, so there's a lot of things going on, but and there's a lot of numbers that float around, but it's all about the carbon emissions that come from construction, right? So when we think of big, large-scale construction, we're dealing with concrete and we're dealing with steel, right? Those are the big materials, or the majority of the materials that go into. I mean, think of any construction project that exists. The foundations are concrete, yeah, no matter what the structural elements are up above, and sometimes the entire structure is made out of concrete. Concrete is just, it's huge. It's like the besides water, it's the and if you think of the volume of water that we use as humans on the planet, for everyday use, concrete is like the second largest resource that's used by humankind, right? Next to water. And so it's a huge thing. And then to make concrete, you got to make cement powder, which that process of creating the clinker, right, they call it, from the limestone and the lime that they have to mine, it requires energy, and that energy emits CO2. And there's the concern how that affects the climate. So and there's different percentages.
Steel is even worse, I imagine.
And steel on a if you compare steel, the embodied carbon is what they like to call it. If you compare steel and concrete on a embodied carbon basis, steel is a lot harder, right? On the CO2 emissions. A pound of steel and a pound of concrete, the pound of steel is going to have way higher carbon emissions, or embodied carbon, in that product. And so all of that combines to an effort to, okay, we want to get more sustainable in the construction industry. How are we going to do that, right? And so, well, let's use wood. That's a renewable resource. It comes from trees. Trees absorb the CO2, right, as they're growing. Plants need CO2 to, what's the process? The photosynthesis, right? When they create sugars in the photosynthesis process that they go through, they absorb CO2. So the thought is, well, if we use more wood in our construction, it's a more sustainable way of constructing
That
things.
makes sense.
Yeah. So that's the impetus.
Well, let's talk about the importance of this test and maybe the science behind the shake table. But could you, I don't know if you know any of the technical details that went into building this type of test? Is this a test that is typically always done for skyscrapers of any magnitude? Why is this one such a special or a significant test that they did?
Well, shake tables are usually, they're designed for lighter structures, right? They can't put a big, they can model, they can do tests on, littler moment frames, concrete moment frames and steel moment frames and smaller things. They can't really do necessarily full scale tests on this table of the heavier type structures, concrete and steel. But for wood structures, it's ideal, right? And so when they upgraded this thing, it was originally designed for the smaller single family residential type projects, right? Your 1 and 2, maybe 3. They could get up to some higher stories, but the table was designed for the smaller structures. And so when they decided to go CLT, the upgrades were just to accommodate this bigger structure, is basically what it is. And so they had to upgrade the weight capacity, right? So the hydraulics and all the actuators under this table that get it shaking. They had
So the fact that they built it 10 stories tall is probably never been done before.
Yeah, I don't think that had ever been done on a table like this. So just to accommodate the additional weight, and put the right hydraulic actuators and stuff under this table, it required an upgrade. So that's what they did.
And do we know anything about the magnitude of the earthquakes that they were throwing at this thing? I remember reading that they have done over 100 seismic events now on this structure, and it's still standing, which is pretty amazing.
Mm-hmm.
But do you know anything about the magnitude of which they're testing? I imagine they're starting small and going up to a certain...
Yeah, they try to emulate usually they try to stick within what the code prescribes, right? So there's 43 and 70 and 72 year return periods. Usually the design basis, right? And so if you translate that into Richter scale type measurements, which I think is what everybody's mostly familiar with, you start getting into the 7.0s and the 7.2 kind of magnitude earthquakes that they're the big events. They start getting into those ranges, and it's all measured in acceleration, right? It's the accelerations that they're trying to control as they emulate these seismic events. And so they just use those ASCE 7 design bases for figuring out what the return period is on a certain level of earthquake, and then they emulate that on the shake table.
So I guess what's impressed you about this test and the results of it?
Well, I'm first of all, the whole thing with wood has been the fire resistance over the years, and so it's impressive that with the CLT technology they've been able to Underwriters Laboratory, right? The UL guys, they're the ones that test products for fire resistance. And so it's impressive that they've been able to come up with longer, I think, and it's because the wood is a lot denser when they make them into CLTs, and it develops a layer of char, they call it, around the perimeter when the CLTs are subject to a fire, and before it starts compromising the cross-sectional properties of these CLTs, as the fire kind of penetrates the cross-sectional area, the char kind of helps slow that down. And so they're still getting 2-hour fire ratings out of some of this stuff, which is impressive. And so that has nothing to do with the shake table, of course, but that's the first thing that's kind of been addressed, is this fire issue, and they've gotten past that. So now it's like, okay, well, let's see what this thing will do seismically, if we can design this thing to resist a significant seismic event. And so what's cool is the lateral systems that they've come up with on these things. So they call them post-tension mass timber rocking walls. And they essentially emulate a shear wall in that the wall is still made of CLT, but they post-tension the ends where you would have a boundary element, right? When a building gets shaking back and forth, you have to have these boundary elements that resist compression as the building's on one side and then tension on the other side, right? And then as it shakes the other way, those boundary elements are taking a compression force next on the other side, and the tension transfers over, and then all of the shear gets transferred into into kind of the panel of the shear wall. And so they've been able to emulate that structural action with these post-tension rocking walls. And so instead of like threaded rods, which are typically used in timber construction on lower rise type construction, instead of these threaded rods, they use post-tensioned cables. They use tendons that they stress after the wall is built, with special anchorages on the top and the bottom, and it puts a pre-compression on that wall, but they can get the lateral resistance that they need from those shear walls using these post-tension mass rocking walls. They're kind of cool looking.
So I think we've discussed a couple issues, I guess, then with tall wooden structures as they're faced in kind of earthquake-prone areas. Are there any others that this experiment addresses? Were they able to, I know they mentioned a drift percentage, but are there any other unique challenges of a tall wooden structure that
so
address?
I mean, in any structure that they're trying to design seismically, right? The drift is a big issue, and so drift is limited by in the code by importance factors and different things. But so, like for instance, like an importance factor is going to be a lot higher for a hospital, right, or a school, or an essential structure that needs to be standing after a large seismic event. And then the importance factors drop off for other type structures. But and I'm losing my train of thought here, Isaac, but what they're trying to do is limit the drift with the seismic design. And it's not just for a lot of it is, it's not just for comfort, right, of the occupants. They're trying to keep the building within an envelope of deflection, so that it doesn't impose too much stress on the lateral system and the I guess the structure as a whole, right? If you have
trying to keep that to 2%.
Yeah, so you're trying to limit to the 2%, and the stuff with the higher importance factors have even less. It's like 1%, right? Yep. So, and so with the CLT and the shake table they modeled all of this in a computer before they actually implemented the test, and they were anticipating as much as 3% drift in some cases, because wood is connected with steel hardware still, right? And all of these elements, they're not continuous. They don't have the luxury of like a cast in place concrete type building. There's different, as you look at the load paths that type of structure has, and it's kind of a monolithic nature to the construction, meaning that all the members are continuous. Even though we make construction joints and we stop construction at each level, things are continuous across columns, across beams. And so that load path has some continuous things to follow as it goes down into the ground and into the foundations. With wood construction, it's all connected with steel hardware, right? Mm-hmm. You got knife plates and things have to be bolted up, and then the cross-laminated timbers have to be butted together, and you've got steel hardware that connects everything. Well, all those joints create give, right? And so joints can rotate, and things can move a lot more. And so that it tends to increase the amount of drift that a building would have. And so, given that wood has all these connections, they anticipated a lot more drift than what they ended up with, right? So, the test they did, they were still within that 2% range. So that was kind of a surprising finding that they had was, hey, we're still within the drift limits that the code prescribed. even though we thought all of these joints and everything were going to move a lot more and things were going to be worse than
awesome.
than what actually happened. So that was kind of a big deal. That was pretty big finding that they had.
How do you see this test and the results of it? How do you think it might influence building codes or other regulations?
Well, I think it's going to make people, the design community, a lot more comfortable with CLT. And so because, I mean, quite frankly, a lot of the things that get designed and the reason why the construction industry sticks with the materials that we've used for, hundreds of years is because there's a level of comfort with those materials, right? There's been, millions of designs that have been generated over the years and they've performed, right? There's always isolated instances where things haven't performed and adjustments get made and after studies are made. But in general, there's a level of comfort, right? And so when something changes and a new system is implemented, then the design community, not only does that new system have to get essentially codified, because that's like the first thing that needs to happen before the design community develops a level of comfort with the system in the first place. And so all of this is going to help things get codified and help the design community, the structural engineering design community, to develop a higher level of comfort with this stuff. And that'll translate into more and more designs implementing this system is what's going to happen. So, that's what I would say is it's going to be more comfortable for the design community.
Well, we've talked a lot about the benefits of wood, I think, and how it can improve. Sustainability is a big deal here. What are some drawbacks then to using wood? I know you just mentioned experience level with using it with a material, but other drawbacks that you can think of with using wood?
Well, there's a big one right now. It's the cost. So I have priced a couple of projects where they were designed with traditional materials, concrete or steel. In fact, the last one I looked at was a parking structure that was, of course, designed with post-tensioned concrete. It was a long span beam and slab type project, and we converted it to an equivalent CLT system, and the CLT was about double the price when I got all done. Yeah. And so when I presented that to the ownership that I was working with, that was a tough pill to swallow, right? That's just like, wow, we need this facility to service our clients, and I can go with a conventional design, which is half the cost of the CLT design, which, maybe more sustainable, but as far as construction goes, but it's expensive, and it's a tough pill to swallow. Now,
is it material cost or labor?
Yeah, it's the fab cost of the material that drives that. And so as CLTs become more and more common and there's more competition in the marketplace for different manufacturers, and there's several manufacturers. Most of the expertise in CLT is, I think, still over in Europe. It's starting to get over here more and more. In fact, the manufacturers here are concentrated in the Northwest area. So up in the Washington, Oregon, where there's a substantial timber community up there. And that's where most of these companies are originating, at least here in the United States. But it's still kind of a niche kind of a market, right? There's just not a lot of competition for these guys, and which tends to drive prices down. But it is really a specialized material. Some of the stuff that these guys sell is still proprietary, so there's additional costs for some of their connections and stuff that are proprietary to their systems. But as this stuff gets, as CLTs get more and more common, then those prices will obviously start dropping. And as manufacturing and fabrication and processes improve, get more efficient, it'll get cheaper. But that's the big obstacle with this stuff, is it's expensive.
Well, awesome. Well, this has been awesome talking about this this whole Tallwood Shake Table Test, the future of wood in higher skyscraper type of construction. Is there anything else you'd want to add about either the test or the direction we're headed with wood?
Well, yeah, and this is more like mid-rise stuff still. I don't think we could get a full-on skyscraper yet, but I don't know. It's just, it's cool to see the market responding to perceived need, right? And
what's the highest you think we could go with wood?
Well, in Europe, they're getting pretty high. I think in Europe, they're up to 25 stories, I want to say.
25?
Yeah, in wood.
Wow.
They're getting up there. And so they're, you know, we can't go skyscraper levels yet, but yeah, I think it's cool to see. I like to see, you know, free market type things take action, right? And so when there's a need in the market, then people are, their ingenuity kicks in, and the entrepreneurs that are out there start trying to create a product that fills a need, right? And so there's a need for this stuff. It's getting off the ground, and it's just starting out, which is why it's so expensive. But it's cool to see people putting their research efforts, universities putting their research efforts, and then the market reacting to needs that are out there, and then trying to come up with solutions. It's kind of cool to witness that, right?
Yeah.
I mean, because the products that we use nowadays that we think are just common, I mean, they had their origins like that as well. You know, you think of, I deal with a lot of reinforced concrete projects, right? And so I think back to some of the origins of those days, and back in the early 1900s, when reinforced concrete was really getting developed in the systems that they use nowadays. Fire was the big issue, right? And so it was like, how are we going to create a system that won't burn down? Well, let's make it all out of concrete. And so that was kind of the impetus out of, by which a lot of the stuff that we see nowadays got created. And so we're kind of witnessing a newer system. I mean, wood's not new, but the way they're fabricating this stuff is. Yeah, so it's cool to see that, like, in its infancy, and get that's what I'm saying.
Well, we'll give a big shout out to Dr. Sheiling Pei, who is an associate professor of civil and environmental engineering at the Colorado School of Mines, who was the principal investigator of running that test. So the Tallwood Shake Table Test, go look it up if you are further interested in this test. It's called the Tallwood Shake Table Test. Go look that up. I think the journey to learn more about the world of seismic testing and tallwood structures is kind of fascinating. So we definitely wanted to talk about it and learn about a little bit more about the direction we're headed with tallwood structures. So Mark, thanks for joining me again on another awesome podcast.
Okay. Thanks, man.
All right. See ya.
Yeah.